So, what is a digital twin and how is one created? Let me show you using a demo of the work we have recently completed with our partner, PTC. First, a bit of background. Our demo focuses on a digital twin of an electric motor. There is no intelligence from sensors embedded in the motor, so we have added a PLC and voltage conducer to measure current and voltage as the motor is running. We can add loads to the motor via the solenoids. It is very important to understand that there is no physical sensor for temperature on the motor rotor. So we need to create a virtual sensor in order to know the temperature. We started with ANSYS Maxwell in order to do an analysis of the thermal properties of the motor. The resulting 3D physics simulation was used to detect and compute the maximum winding temperature of the motor. Next, we used ANSYS Workbench to create the reduced order model with current as input and maximum temperature as output. Here are a few of the actual 3D simulations of the motor that we created. The ROM of the motor is brought into our system simulation platform, ANSYS Twin Builder, to create a digital twin of the electrical part of the motor. We measure the current coming from the motor and in real time calculate the temperature of the motor through the virtual sensor. We can calculate the temperature of the rotor, stator, and case to determine the remaining lifetime of the motor. We can also use the digital twin to help with predictive maintenance by determining the future temperature of the motor based on the various loads and currents. Now we can validate the digital twin. To do so, we need to gather information from the actual motor through PTC ThingWorx. We start the ThingWorx agent and run the simulation in Twin Builder. Information on current from the physical asset is sent to Twin Builder, where the simulations are run to determine the current temperature of the motor along with the future temperatures. On the left, we can see the future temperature calculation in red and the ambient temperature in purple. This information is passed back to ThingWorx. Now we can apply a load to the motor and we see the values changing, and the future temperature is increasing while the remaining lifetime of the motor is decreasing quickly. This is how we validate a digital twin in the design phase. Now we can generate the digital twin runtime code that we add to ThingWorx through the connection agent. This provides ongoing predictive maintenance capabilities on the physical motor. Now that the runtime is added to ThingWorx, let's take a look at all of the cool stuff an operator can access. Here's the motor in ThingWorx along with information on input from the virtual sensors. We can see the current motor temperature along with the future temperature if the motor continues to run in its current state. Remaining lifetime of the motor is also available along with time to critical temperature of the motor. And in this view, we can dive a bit deeper into the motor conditions to look at the temperature range of the motor over time. Why is all of this information important to know? Motors can be expensive and downtime of a motor can cost even more. If operators are able to predict when the motor may fail, maintenance and replacement schedules can be adjusted accordingly, saving time and effort. Imagine the savings that will be realized by implementing digital twins.